Well, we are actually surprisingly close to the end of our journey of understanding enough of this paper to get to the point where we can talk about Maxwell's equations being written down as one expression. Remember, we were trying to see if we could squeeze all of Maxwell's equations down to a single expression, and to that end, we decided to read this paper because that would get us there. Turns out this paper brings us a lot of other things, and we have been diverted a bit in this section here, Pauli and Dirac matrices and the spinor representation, where we took a bit of a diversion into how geometric algebra handles quantum mechanics. What we really need to do is we need to get to somewhere in here in space-time calculus, and then it says Maxwell's equations in a vacuum. And most of this we can ignore as far as our goal, which is just to write down Maxwell's equations in a single line. We don't need to go through all of the rest of this material, although we probably want to write down an expression down here. So my plan now is I need to finish up a few comments about quantum mechanics and geometric algebra because I sort of opened the door to that in the last lesson, and the taste that I provided was probably enough to confuse, or not, I shouldn't say confuse, but enough to whet your appetite enough to say, hey, I'd like to see just a little more of that. So today we're going to do just a little more to get to the end of this. And then I'm hoping that I can do maybe a single lesson in space-time calculus and get to the end. Maybe this is our last two lectures. We might need 3. But just to be clear, we're not going to go through this entire paper as good as it is. We're just trying to get to that one goal where I can write down this as representing all of Maxwell's equations inside of geometric algebra. Right? That was always our goal for the start of this mess, and it was a diversion to begin with. So today we're going to just talk a little bit more about quantum mechanics in geometric algebra and maybe start a little bit of the space-time calculus piece. Okay, so let's begin. So in the last lesson, we endeavored to make sure that we weren't confused or thrown aside by this notion of a spinor. And in quantum mechanics, of course, a spinor is this invented concept that's designed to give an electron essentially a magnetic moment and thereby an associated angular momentum. And the history of the invention of a spinor is actually pretty fascinating. But it comes down to creating these two-dimensional complex vector spaces that we attach to wave functions. And if we get rid of the spatial part of the wave function, because normally there would be, some sort of spatial part, right, attached to this, maybe even a time piece to it. And it becomes a tensor product space of this piece, which is the state associated with the spin, and this is the state associated with the spatial position of the particle. And usually there's some kind of tensor product in there. But if forgetting all about the spatial part, just examining only the spin part, the history has always been to give us spinors in this form. It's two complex numbers, which we showed in our last lesson can be broken down into its 4 real numbers, A0, A1, A2, and A3. And once we have those 4 real numbers for any spinor from regular quantum mechanics, we can write it down in this geometric algebra form by just planting these numbers in exactly the right places, right? Where these 3 numbers here, I don't want the i's. Hold on. I want just the numbers without the i's. And those 3 numbers go here. And then this is it's a relative bivector. And it's a relative bivector because it's in the relative space where the 3 spatial vectors are sigma 1, sigma 2, and sigma 3, right? Where we have it's a 3-dimensional geometric algebra. In that space, this is the dual of a vector, which is a bivector. So this is going to be I sigma k is going to be a bivector. But what's interesting is that a bivector of these three guys, when you understand the definition, where sigma 1 is gamma 1, gamma 0, sigma 2 is gamma 2, gamma 0, and sigma 3 is gamma 3, gamma 0. If you have any bivector in the three-dimensional algebra, for example, sigma 1, sigma 2, that becomes sigma 1, gamma 1, gamma 0, gamma 2, gamma 0, right? And you flip these two around, you pick up a minus sign, you get gamma 1, gamma 0, gamma 0, gamma 2, which is, and remember, gamma 0 squared is going to equal 1. So it's minus gamma 1, gamma 2, which is gamma 2, 1, which is also a bivector in the space-time algebra. So it is also a space-time bivector. And I say this because you read this a lot in the text. You'll say, oh, it's a relative vector, a relative bivector, or it's a space-time vector or a space-time bivector. And here, whenever they say the word relative, they're always talking about 3D geometric algebra that's a subset of, or a sub-algebra of the four-dimensional space-time algebra. Okay, so with that in mind, we now understand that this is the geometric algebra interpretation of a spinor. And I didn't do this last time, but you can actually break this down if you take A0, A3, I1. That's sort of the psi 1 piece. And then if you go minus I sigma 2 times A2, A1 sigma 3? Hold on. Oh, no, that's right. A1 sigma 3. So it's a kind of a weird form, but this piece here would correspond to psi 1, and this here corresponds to psi 2, which of course is true. You have A2 and A1, which are part of psi 2, and then you have A0, and A3, which are part of psi 1. Okay, so that's where we stop. So we stop with this great understanding that any spinor can be written in the space-time algebra. But the part I just want to flush out is not in this paper, and it's a total diversion, but just one lesson's worth of time, is what about the basic operations of quantum mechanics? What's so good about all this, if anything? Because I'm not so sure it is that good. And when I say that, I'm being a little glib, right? I'm no expert in how geometric algebra has evolved or all of its uses. I'm learning it probably just a little bit ahead of you guys if you're following along, or if you've been following along continuously, you may even know more about the subject than I do. But right now what I'm thinking is, okay, normal physicist thinking is like, this is pretty simple, right? Organizing data into matrices, I mean, that's good news. You can run it through a computer, complex numbers, that's not confusing. We understand how that works. Why bother with this form when we have this form? And the answers seem to come in from a couple different angles. Usually the answer that I'm hearing is, well, first of all, this is all real. A0 and AK are real numbers. Here you're having two complex numbers. But of course, quantum mechanics is all about complex numbers. I'm not sure why I should be reluctant to engage fully with complex numbers, take advantage of their structure and build my models out of that. So there's that. But there is something to be said about everything is real here. Okay, I get that. What I think is a little more compelling of an argument has to do with these basis vectors. In the geometric algebra, we know what these guys are. These in the three-dimensional geometric algebra represent directions in space-time. Unambiguous, this is, sigma 1 is pointing in the x direction, sigma 2 is pointing in the y direction, and sigma 3 is pointing in the k direction. And we understand them to be basis vectors, and we know their dot product relationship, their orthonormal, in the circumstance we're dealing with at least, and case closed. There's no ambiguity about what these are. And the algebra of these basis vectors inside the geometric algebra is extremely clean and obvious. When it comes to working with spinors, however, spatial directions don't really come into play. What does come into play are operators, also given by the letter sigma, the Pauli operators, and they are given a direction associated with them, right? But we never call them basis vectors. What we do is we call them operators. And they're operators in the sense that they're linear operators that act on a vector space, in particular the vector space of spinors, of two-dimensional complex spinors. Remember, it's two-dimensional because it's a complex vector space with two complex numbers. So it's two-dimensional complex vector space. You could think of it as a four-dimensional real vector space if you wanted to really bend the nature of the matrices around and come up with a bunch of rules that compensate for everything. But it's a two-dimensional complex vector space. So these guys take elements of a two-dimensional complex vector space and return you other elements of that vector space. They sit outside of the vector space. They're linear transformations on the vector space. Now here, it's not really the same thing, right? These sigmas are elements of the algebra, and the spinor itself is also an element of the algebra. So if I was to hit this thing with a Pauli matrix, I would come back with another set of four complex numbers in another spinor. If I were to hit this thing with a basis vector, right, inside the algebra, it would just turn, for example, say I hit the whole thing with sigma 2, right? Put sigma 2 here, just like I was going to do here, sigma 2. This sigma 2 would return a different vector after I did the multiplication out with the I guess I have to say that, right? These sigmas will have a matrix representation of a linear transformation that will convert these guys. So I need the matrix representation of sigma 2, which in this case would be sigma y, which would be the second Pauli matrix, which we'll talk about in a moment. And here it's just a basis vector, so I get A0 sigma 2, then I get AK sigma 2I sigma k for each value of k, which I can calculate out. So I just run through the algebraic properties. But this is an element of the algebra, and this is an element of the algebra. And of course, the product is an element of the algebra. And we know that because the product itself is an algebra. The whole structure is an algebra, so it has to be closed with all of its algebraic products. So there is a certain simplicity to this where I'm now just using, if in fact these guys are correlated with these guys, right? If there's some correlation between these operators and these basis vectors, then it does seem like this is, we're now thinking in literally terms of spatial directions, as opposed to this sort of mystical operators, which, by the way, go back to the core of quantum mechanics. It is an axiomatic assumption of quantum mechanics that Hermitian operators represent observables, and the values of the observables are eigenvalues of the operators, and they operate on a linear vector space. All that is axiomatic. Inside this algebra, the notion of an operator doesn't really appear. It's just another geometric product. We just have to make sure we understand how we can get quantum mechanics out of all that. So that's sort of an interesting idea. The other part here is I wrote down, good enough. So now the question is what is the connection between these basis vectors, which we've written as sigmas, and these Pauli operators, which are also written as sigmas? That was done intentionally, of course, just like gamma for spacetime algebra is going to, the gamma mu's of the spacetime algebra is going to link up to the gamma mu's of the Dirac equation, right? Those were intentionally chosen that way because these are in one-to-one correspondence, in fact. So this is in one-to-one correspondence with sigma 1, with sigma 2, and with sigma 3. So let's see how that works. And we're supposed to go, wow, this is strangely coincidental. But if we know about the Pauli matrices, you know that they obey all the rules here on this screen, right? The square of each of the Pauli matrix is the unit matrix, right? So in matrix terms, which is what I probably should have used, this is a 1-1 matrix here. And these Pauli matrices, in case you've forgotten, are these three matrices. We could use this representation of the Pauli matrices. There are other versions of the Pauli matrices, but this is the most commonly used one. So if you took this matrix and squared it using regular matrix multiplication, you'd get the unit matrix. Likewise for sigma 2 and sigma 3, and also likewise for minus I, sigma 1, sigma 2, sigma 3. Now, however, right away you can see, well, wait a minute, in the geometric algebra, in the space-time algebra, or in the relative algebra of the space-time algebra, right, the sigma 1, sigma 2, and sigma 3, that works out just fine as well, because what we see there is we see, what do we see? We see this chain of logic, right? Sigma 1 is gamma 1, gamma 0, sigma 1 squared, gamma 1, gamma 0, gamma 1, gamma 0. You flip these two gamma 1, gamma 0s, picking up a minus sign because of the anti-commutativity of these basis vectors. And you have gamma 1 squared, gamma 0 squared, but gamma 0 squared in the space-time algebra is 1, but gamma 1 squared in the space-time algebra is minus 1. So you end up with the real number 1, right? So in the Pauli, in the quantum mechanical formulation, you end up with the matrix 1, which I guess we could write with sort of double bars on it. But in the space-time algebra and in the three-dimensional relative algebra, we get the number 1, right? Yeah, we could have skipped all this, by the way. All you have to do here is you just have to remember that sigma 1 squared is 1. Actually, for the relative algebra, sigma I squared is 1, right? They're all equal to 1. It's not a mixed algebra or a pseudo. It doesn't have a pseudo Riemannian metric. It has a regular Riemannian metric. But what's also fun is this. This is very telling because in the relative algebra, that would translate to minus sigma 1, sigma 2, sigma 3, right? Because remember, that's what I is in the relative algebra. It is the pseudo-scalar, right? Or the basis of the pseudoscalars. And then you have sigma 1, sigma 2, sigma 3. And then you just start your crazy commutations, right? This one comes over negative 1, positive 1, and then it clears. So you have minus sigma 1 squared, sigma 2, sigma 3, sigma 2, sigma 3. And then you flip these two, and you have minus sigma 1 squared, sigma 2 squared, sigma 3 squared. But you had an additional minus sign because of this flip here, right? And that equals 1, right? So now what you're seeing is that this is very interesting, right? The I of geometric algebra, right, of the relative geometric algebra that involves the basis vectors sigma 1, sigma 2, and sigma 3, that I is related to the imaginary number I that existed in quantum mechanics. Well, wow, that actually kind of is interesting, right? Because now this I, which sometimes appears to be quite an arbitrary thing in quantum mechanics, you really have to peel down into quantum mechanics to see why these I's show up. And it has to do ultimately with, how transformations are done and the exponentiation of Hermitian matrices and things like that. And you see that the I comes in there to change between anti-symmetric and symmetric stuff, and it's buried way in there. And even then, it's just put in there sort of as a mathematical convenience. But now, all of a sudden, if you take seriously the relationship between the Pauli matrices and geometric algebra, that I suddenly becomes this pseudoscalar basis vector. And that's really, I think that is pretty interesting, okay? So far we've shown that for this relationship, we can just go one-to-one correspondence, geometric algebra, straight to the Pauli matrix algebra. So that leaves in the Pauli matrix algebra is this famous expression, right? This commutator expression. And it's worth a second to do, right? Sigma 1, sigma 2 minus sigma 2, sigma 1 equals 2 2I epsilon 1, 2, 3, sigma 3, right? So that's going to be 2I sigma 3. So if we were to translate this into geometric, so this is what's true for, this is what's true for the Pauli algebra, the algebra of the Pauli matrices. So if we were going to translate this to geometric algebra, what would we get? Well, sigma 1, this part here, sigma 1, sigma 2, sigma 1, sigma 2 minus sigma 2, sigma 1. Well, that's easy, right? Because we can rewrite that. If we treated these sigmas as the basis vectors of our relative algebra, it would simply be 2 sigma 1, sigma 2 equals 2I sigma 3. And why is that? Well, we know these things anti-commute in our algebra, as they do here as well. And so sigma 1, sigma 2, is that 2I sigma 3? Well, the 2's cancel, right? And yeah, sigma 1, sigma 2 is in fact the dual of I sigma 3, right? And you can just write down sigma 1, sigma 2, sigma 3, right? That is I, and then sigma 3, and then you multiply these two together to get 1, and you're left with sigma 1, sigma 2. So we've just checked one case, but it's pretty clear that this commutation relationship is going to exist using what we learned from this, where this I is understood as the capital I, the pseudoscalar basis vector. And likewise, you can show that the anti-commutation relation is also identical. Okay, so let's begin by looking at some of the regular states that we encounter in quantum computation, or just general quantum mechanics as well. Quantum computation is, in fact, general quantum mechanics, but let's go back to the ones, and using some of the notation you see a lot in quantum computation. We have the up state, the down state, the plus state, and the minus state. And let's see if we can construct those using our rubric. Now, the first thing I want to indicate is there's sort of a progression here. These symbols from Dirac notation, right? These guys here, these bra and their equivalent ket notations, that is really, truly, in my mind, the most abstract form of this. It just says, hey, we're dealing with a linear vector space with two-dimensional linear vector space, complex vector space. And these symbols, they exist no matter what representation we choose. Now, we're going to choose a representation in geometric algebra where I want to be careful. The word representation usually refers to a matrix representation, which would be the Pauli matrix system that we're kind of getting away from. But if I want to cast the state 1 in the geometric algebra representation, I kind of walk through it. I say, oh, I'm going to represent the state 1. I write it down in the Pauli form, and then I look at this Pauli spinor when I'm done, and then I convert it to a geometric algebra. So I'm still my mind is still going from the super abstract through the Pauli formalism into the geometric algebra formalism. And I think the idea is that in a perfect world, we kind of don't even use this, right? The idea is that this is supposed to be it's so superior that we're supposed to kind of get away from this. I'm just not at that level of sophistication with my geometric algebra yet. I have to walk through the Pauli system first. But just keep in mind that that's not always the plan, right? Now, the way I'm going to do this is I'm going to say, oh, okay, so our Pauli vector for the up state is 1, 0, and then I map it into our little rubric here, and I say, well, A3 is 0. There's no complex part in the upper index or in the upper component, and there's no complex part in the lower component. In fact, there's nothing in the lower component, which leaves me with just A0, and A0 is actually 1. So this is all going to give me just the number 1, right? When I figure this out, these guys go away. All that's left is A0, and that's the scalar 1. And so I write down that the up state in the abstract notion is represented by the number 1. Let's make it just a nice number 1. So what about the down state? Well, here's a little foreshadowing what it's going to look like, but the process is identical, right? The down state is, we know it's 0 and 1. And now these two guys go, oops, these two guys go away. The upper part goes away. There's no complex part. So I know that A2 minus A2 equals 1. So A2 equals minus 1. So this is gone. And then all that's left is A2I sigma 2. A2 is negative 1. So I have minus I sigma 2. So now I write that represents, whoops, I'm about to draw a bra instead of a cat, the down state, right? And that's of course what I've calculated right here. Now for the plus state, I can just simply look at this version of the cat, right? I know what the plus state is by definition, right? This is sort of a definition, right? So I'll give it little 3 arrows. And the plus state is 0 plus 1, so boom, 1 minus I sigma 2, and then 1 plus I sigma 2. Where these, notice the signs swap here, right? The signs are swapping. So with that in mind, we have now created the geometric version of all of these states. And what's interesting is that these states are all part of the geometric algebra, just like these are all part of the vector space of quantum states. What we're now going to see slowly is that, well, first of all, one of the states is just a scalar, and another one of the states is purely a bivector, but these mixed states are scalar and bivector parts, right? They have both pieces. And what's interesting now that we'll learn is that in the geometric algebra, all of the operators that act on these states are also part of the algebra itself. Whereas even in this abstract notation, you have the vector space of states and then operators as a separate collection of entities that act on them. So we're kind of bringing those operators into the same space as the states when we do this in geometric algebra. Okay, so what next? All right, so now let's make sure we have a clear picture on how we are going to deal with operators in the geometric algebra that mimics quantum mechanics. And again, we will lean on our understanding of the Pauli system. And that's really what we know. We know quantum mechanics through Pauli matrices and spin one half particles with spinors that are two-dimensional column vectors, right? So we've got to start there. And we know that these guys operate on the vector space of two-dimensional spinors, so they are linear transformations of the vector space. So how does this all translate into geometric algebra? And this is probably the first place where you're supposed to have this aha moment that's supposed to be really, really like, wow, something interesting is going on. Because we've always known that the Pauli matrices are represented by, somehow are connected with spatial directions, right? This would be x, y, and the diagonal one is always z. And so we've associated them with space, but we've never thought of them as literally vectors in a three-dimensional space. But now we actually are allowed to do that. In geometric algebra, we now, instead of this hat for an operator, we'll use this arrow for the moment, showing that this is the direction vector of a three-dimensional geometric algebra, right? This is the 3D geometric algebra. So in this case, all the sigma i's will square to 1, right? There's no negative 1 like there is in the spacetime algebra. We know that it's a spacetime bivector, but when we drop into the three-dimensional form, which is a subalgebra of the spacetime algebra, we can treat it as a vector. So we'll call it a relative vector or a space-time bivector. And that's the language you'll see in the papers, including the one we're reading together. This is a relative vector or grade 1 object, or it's a space-time bivector, which is a grade 2 object. Now, my level of proficiency with this is I frequently drop into the space-time algebra picture to do calculations because I just got used to that from starting with the study of space-time algebra. But what we should do is when we're dealing with just quantum mechanics, we should really be working entirely in the 3D uh, uh, relative algebra, because things are actually much simpler to calculate. So when I feel this temptation, I'm going to resist it. In fact, one of the viewers of the channel pointed this out, saying I was making it hard on myself because I was constantly going back to the space-time algebra to do the calculations. There's a bit of a tension there, right? I want everybody to remember that we are dealing ultimately with the space-time algebra, and I want people to say, hey, look, when you break it down to its essential components, you can solve the problem that way. Uh, Otherwise, you start having to remember a lot of things. But it's hard to tell if it's really a lot of things, because when you do the Pauli algebra, you're remembering a lot of things too. You're leaning on a lot of skills you learn from linear algebra and just quantum mechanics. I don't know how big of a memory block that is. So it's hard for me to say that it's unfair of me to say that, oh, geometric algebra and spacetime algebra is more or less tedious. It feels that way to me right now, but it's just a matter maybe of familiarity. Anyway, so um, we showed the operators of the Pauli system are going to just be immediately simply the vectors. So we lose all of the matrix mathematics and the matrix mechanics, but these guys, as we showed a little earlier, have behaviors, commutivity, anti-commutivity, and very similar or identical, isomorphic would be the word, to the Pauli matrix, the Pauli operators. Then as a reminder, we just went through this spinor thing. I did a whole version of this lecture where I got this backwards, and I don't even know how. I wrote 0 was the up and 1 was the down. It's the most absurd thing. I couldn't believe it when I saw it. And again, a good viewer pointed it out to me, and at first I refused to believe it. I was like, how could I make such a silly thing and go through the whole lecture that way without noticing? So I've redone the lecture. And then, of course, we just went through this a moment ago. An important point to understand is the pseudoscalar is the same as sigma 1, sigma 2, sigma 3. It actually, if you work this out and you calculate all these gamma matrices together, these zeros all go away except for 1, and you end up with the same pseudoscalar as in the space-time algebra. So that's kind of interesting. A convenient thing to remember is that the pseudoscalar commutes with space-time bivectors, which means it commutes with relative vectors. So this is something we can lean on to simplify our calculations. Otherwise, I would be breaking this down into gamma 0, gamma 1, gamma 2, gamma 3, and then gamma 1, gamma 0, and then I'd be commuting all of these things and trying to figure out whether it commutes or not. It's better to just remember that the pseudoscalar commutes the way it does, and that makes things a little bit faster. And let's see, we did this a moment ago. I just want to show you redundantly a little cleaner version of it, that this translates to this, and that allows us to calculate these A's, and then using this matrix here, we figure out that the up vector is just given by the scalar 1, and then the down vector, as we did before. Now, the thing about the down vector, remember, is it's given by minus I sigma 2, but what is minus I sigma 2? Well, we could blow that up. We could say it's minus sigma 1, sigma 2, sigma 3. Make one commutation, which brings in a minus 1, which kills that minus sign. In the relative algebra, all of the vectors square to 1. So you end up with sigma 1, sigma 3. So the down state is actually a relative bivector, right? It's a relative bivector, and it is... And well, what is it in the spacetime algebra? Well, that would be gamma 1, gamma 0, gamma 3, gamma 0. I make one exchange, and I get gamma 1, gamma 0 squared, gamma 3. That one exchange gives me a minus sign. Squaring gamma 0 is plus 1 in the system we use. So this is equal to gamma 1, gamma 3, which is equal to gamma 3 1, or minus, no, I'm sorry, minus gamma 1, gamma 3, which is equal to gamma 3, 1. So it is a space, so this is also a space-time bivector, right? Interesting, right? It's a space-time bivector, but it's not one of the sigmas because it doesn't have a time component here. So this is a relative bivector and a space-time bivector. All right, so now let's study exactly how these operators function. So your standard Pauli operator acting on a quantum mechanical spinor state in the Pauli form is got this representation. There's some matrix here that represents this Pauli vector. We'll just keep it totally general for now. This is the spinor representation of the ket. And you simply do this matrix multiplication and you end up with another two-dimensional spinor, right? With the sum at the top and the sum in the upper component, and the sum in the lower component. Now the rule is to mimic this operation in geometric algebra. The rule is that we take our geometric algebra representation of the spinor, right, which is going to look something like this. It's going to have a real part and then this relative bivector part, right? Because remember, I sigma k gives us a bivector. So it's a relative bivector because it's in the three-dimensional space, right? It's also a space-time algebra bivector, but we call it right now a relative bivector. So we take this spinor piece, we give a geometric product on the right with sigma 3 and a geometric product on the left with the equivalent geometric algebra representation of this operator, which is just the spatial relative vector in the direction of that's associated with the Pauli matrix. So if this is Pauli z, or Pauli 1, we would take this to be sigma 1. And we just make this little geometric product here will always end up giving us a new structure that has the same form as this, but that new structure will mimic this guy right here, right? And demonstrating that, this is, I just want you to accept this for now. Now it seems weird, right? It seems like it's a little out of balance. Like, why is there a sigma 3 if we're trying to find the operator form for sigma k, why is there always a sigma 3 on the right? Why does that happen? And that happens actually a lot in geometric algebra, is one of our directions sort of becomes an orientation that flows through all of our math, and you end up with these things that feel like they're asymmetrical, but they're still fully general. But ultimately, any coordinate system, you're picking a coordinate direction, right? And that's what's going on here. Even in the Pauli system, sigma 3 is diagonal, right? And that favoritism just shows up in this case right here. So that's one rule, right, is to operate on our geometric algebra version of a spinor. We multiply on the right by sigma 3 and on the left by the operator form. And of course, this extends by linearity to more complicated operators, which we'll show in a moment when we demonstrate the Hadamard gate. Then there's this other thing. If I want to take a state and multiply it by the complex number I, right, I still get I can do that, right? Any state, this is just a member of a linear vector space, and this is a scalar in that vector space. It's a complex vector space. This is a complex number. So I can do that multiplication quite trivially, but in geometric algebra, it is a little bit trickier in the sense that this is the prescription. If I want to find the equivalent geometric algebra spinor that represents the spinor multiplied by the complex number I in our Pauli work, I have to multiply on the right by I sigma 3, which is multiplying on the right by a relative bivector. And so let's just do a quick example, right? So if I took the up state and I wanted to operate on it by the Pauli operator sigma 1, I would normally just do this matrix operation, which flips the two components and gives me the downstate, right? Gives me the downstate. I've had terrible trouble with up and down states in this lecture. Oh my God. gives me the downstate. I'll put it in red just to remind myself how imperfect I am here. But the equivalent form is, well, the up state in our geometric algebra representation is just the real number 1, right? That comes back from what we did right over here, right? The up state is represented by the number 1 using our prescription. And so I multiply on the right by sigma 3 according to this operation, right? This sigma 3 here comes right to there. And I multiply on the left by sigma 1, which is here. So I get sigma 1, sigma 3, which is minus I sigma 2, which I know is the down state, right? Is the down state. So these two match, and our formula is validated at least for this condition. Now, likewise, I can take sigma 1 on the down state. I can exercise it through the Pauli system, which, again, just flips the two components, and it should give me the, oops, look at me do it again. I'm going to punish myself with red there. And I converted the down state to the up state using the sigma 1. And now I have a little bit of more of a trick because the down state is minus I sigma 2 in the geometric algebra prescription. So I multiply on the right and the left as per the formula for how to operate with a Pauli vector. And now I blow this whole thing up. Now, this is probably where I'm making things harder for myself than I should, right? This is sigma 1, this is minus sigma 1, I sigma 2, sigma 3, right? Which I know that I commutes with all of these relative vectors. So this is minus I sigma 1, sigma 2, sigma 3, right? And sigma 1, sigma 2, sigma 3 actually is I. So this is minus I times I, which is minus I squared, but I squared is famously negative 1. So it's minus negative 1, which is 1. And you could blow the whole thing up by expanding I into its own sigma 1, sigma 2, sigma 3, realizing, oh, that's I1 squared. Then I have to make one commutation here, picking up a negative 1, but then sigma 2 and sigma picking up a negative 1, which gets rid of this negative 1, and then realizing that everything squares to 1. And 1 is our representation of the up state, right? So it is obviously a little faster if I remember, hey, this commutes, and I recognize that that is I can do it much quicker. So that's the kind of thing where, the more you do this, the more you develop those intuitions, and the smoother this process becomes. But for me right now, it's not a very smooth process at all to do all this work in the geometric algebra formalism. Just remembering these rules, right? Having to remember this rule is a whole new rule. Matrix multiplication, I know that cold, right? Okay, but let's look at it in general, just to sort of prove the rule. Let's try that. Well, the steps are pretty obvious, right? I just take a general form of a spinor, and I know that how to convert it to a geometric algebra object. And here it is, right? It's the obvious A0, A1, I sigma 1, A2, I sigma 2, A3, I sigma 3, where each of these coefficients is derived directly from whatever spinor I've chosen to work with. So just to be absolutely clear, of course, the top is Pauli, and then from below this line is all entirely geometric algebra. So once I construct this as an arbitrary spinor right here, right? And once I construct that, well, the rule is multiplying the left by the operator, which I don't want to call it an operator because it's not. It's a spatial vector, right? It's a spatial relative vector. But it's the one that, in my head, I'm thinking, okay, quantum mechanics, I want to use the sigma 1 Pauli operator on my spinor, right? But I just multiply on the left by the spatial vector using a geometric product. And then on the right, I multiply by sigma 3. That's part of the rule. So what is this going to end up being? So I'm going to crunch this out. And I should end up with another object that is constructed this way, but it shuffles these A's around, and that shuffling should mimic this object right here, right? Meaning if I formed the geometric algebra structure of this thing, right, then, where A0 is replaced by minus A2 is replaced by A0, A1 is replaced by A3, and A3 is replaced by A1, then this process here should give me that object. And of course down here you see it, right? A0, well, I just kind of did it. A0 is replaced by minus A2. A1 is replaced by A3, which is exactly what's going on. A1 is replaced by A3. A0 is replaced by minus A2. A0, I should say A2 is replaced by minus A0. So here's A2 is replaced, minus A2 is replaced by A0, same thing. And A1 is, A3 is replaced by A1, which is A3 is replaced by A1. Okay, so ultimately, a little foreshadowing, you can see it all works. But the process of going through this, I'm just multiplying on the left and the right, careful not to screw around with the commutations. And then, of course, here I have the same issue where I kind of make it hard on myself by blowing up the i's. Here, if I just immediately recognize, for example, that this object here is the same as sigma 1 I, right, which is totally just I, right? And then on the right, this comes out, so this ends up being I sigma 3. So instead, I kind of burned up a lot of energy, kind of calculating what these things were and blowing them all up into sigmas. You don't really have to do it, but I've done it here for you in case you wish to see the work, where, for example, this guy here blows up to this thing, this guy here blows up to this thing, and then, everything kind of clears out pretty quickly. And then I'm left with these sigmas here that I have to figure out, okay, what is that, what is that in terms of I sigma 1, sigma 2, I sigma 1, I sigma 2, and I sigma 3. Each one of these that doesn't have it has to be a dual, essentially, of one of these other guys. And finally, when I get all that done, I land here, and it is a match, right? This guy does, in fact, match that guy. And that's sort of a proof of the rule. In fact, that's kind of how you probably generate the rule, right, in a way. But regardless, this is the general way of operating with a Pauli operator on a spinor using geometric algebra. All right, so now let's examine the Hadamard gate. Pretty simple idea here. The Hadamard gate is given by this matrix representation, which is given in this operator representation. So it is the sum of the Pauli 1 and Pauli 3 operators. Remember, this is the diagonal one, right? The diagonal operator. So if that's the operator form, when we can simply plug through with an up initial state, and very quickly we derive a final state that has equal components, and the upper and lower components are the same, and that is reflected in the abstract notation, the direct notation as sigma as the down state plus the up state, and we give that a simple. It shows up so much that it has its own symbol plus. And likewise, if we operate on the down state, we end up with this state minus, where the only difference is this sign difference between these two states here. So that's how you would knock it out in the Pauli system. In our new geometric algebra system, of course, the operator acting on the down state, see, again, I have not totally cleaned up my story yet, right? The operator acting on the up state, I'm punishing myself in red, right? The operator acting on the up state, we replace all of this with our prescription. The operator goes on the left, the spinor, which is now a geometric algebra object, which in our case, because it's the simple up state, is simply just a real number 1, and then sigma 3 on the right. Then we just sort of process this through. This one's particularly easy, right? The 1 is pretty much gone, and then you just use linearity, and you get sigma 1, 3 and sigma 3, 3. Sigma 1, 3 is a relative sigma 1, 3, a sigma 1 times sigma 3. So that's a relative bivector, right? And sigma 3, 3 is just another way of writing sigma 3, which of course is 1. So that goes away. So you end up with 1 over square root of 2 from here, right? This goes to here. And then this, you have to recognize that sigma 1, 3 is actually minus I sigma 2 to put it in the sort of the preferred form. And so when we're all done, we can recognize, okay, that is 1, and that, is, this part here is 0. And something's wrong. Yeah, so, okay, so here's what's wrong, right? What's wrong is the way I write this, I have to write this down a little more carefully, right? It's 1 over square root of 2 times 1 plus minus I sigma 2, right? Which is really, I mean, the same as 1 over square root of 2 minus I sigma 2 plus 1, which this guy is represented as 0, and this guy is represented as 1, right? 1 over root 2, but that's actually the plus state. So that the mistake I made is I put a minus there, but it's actually the plus state. And so there's an example of how you would use the Hadamard gate, right? Okay, what next? Okay, so as far as this paper goes, we're kind of, I want to say, floundering in this area with this massive diversion into quantum mechanics. I'm almost wondering why they chose to put this in the paper. I've kind of looked ahead, and of course it's an important and fascinating concept in geometric algebra. I'm not so sure it's absolutely critical for their subsequent narrative about electricity and magnetism, which goes on after this. I don't think it shows up again after this section here. So the point is, but now that we've started it, I kind of feel like I got to go at least another lecture into this. There's other interesting things about quantum mechanics that since we opened the door, we might as well walk through it a little bit. Look, I'm in no hurry of getting to the end of this, and I'm not constrained in any way, so we'll take it up from next time. I do think one more lecture regarding the geometric algebra of elementary quantum mechanics. We won't go into the Dirac equation, for example. We'll just stick with just the basic operations of elementary quantum mechanics, get that past us, and then finish up. Okay, I'll see you next time.